This video is about absorption spectra. To understand how an absorption spectrum is formed, we'll start with a gas cloud, just as we did for emission spectra. However, this time, we'll begin by shining white light onto the gas cloud. Before we go further, just a quick reminder here that white light is composed of all the colors of the visible light section on the electromagnetic spectrum. Now, after the light emerges from the gas cloud, it is passed through a glass prism and forms an absorption spectrum on a screen that is placed behind the prism. Here's an example of an absorption spectrum. Now, if we use the same type of gas and carry out an experiment like we did in the previous video for emission spectra, we'd get the following emission spectrum. As a reference point, let's set the full electromagnetic spectrum for visible light. As you can see, the absorption spectrum is almost the same as the full spectrum, except for the 6 vertical black lines. The key here is that these black lines occur exactly at the positions where the 6 colorful lines appear on the emission spectrum. Maybe you've already guessed what is happening here, but let's just take a moment and use an energy level diagram to discuss in more detail how an absorption spectrum is formed. Another way to say that white light is composed of different colors is that white light contains photons of different energies. As we learned earlier, photons towards the red end of the visible spectrum have lower energies, while those towards the violet end carry higher energies. Also recall that energy levels in an atom are quantized, which means that in order for electrons to transition from a lower to a higher energy level, they must receive a specific amount of energy all at once. Now, a key point here is that some photons in the white light carry exactly the right amount of energy for a given electron transition to happen. The energy level diagram here has the following 6 possible transitions. This means that in terms of energy, there are 6 different types of photons in the white light that can cause an electron transition, in other words, that can be absorbed by electrons in the gas cloud. Therefore, the photons that have one of these 6 different energy values will be absorbed by the atoms in the gas cloud, and as a result will not reach the screen. These missing photons are the reason why we get the vertical black lines in the absorption spectrum instead of getting the full visible spectrum. Each arrow that you see on the energy level diagram corresponds to one of the black lines on the absorption spectrum. Logically, the longer the arrow, the more energy carried by the missing photon, and the closer the corresponding black line will be to the violet end of the spectrum. As for the emission spectrum, of course it makes sense that the colorful lines appear exactly at the positions of the black lines above, because when the electrons in the gas atoms transition back from a higher to a lower energy level, they emit photons with exactly the 6 different energy amounts that were absorbed earlier. Let's now briefly summarize what we just discussed. We began by recalling that white light contains photons of all energies from the visible section of the electromagnetic spectrum. We added that energy levels in an atom are quantized, so electrons in the gas atoms must gain a specific amount of energy in order to transition to a higher energy level. Therefore, when white light is shown on a gas cloud, photons that correspond to the specific energy amounts are absorbed by the electrons in the gas atoms. Logically, the photons that are absorbed do not reach the screen, which is why we see black lines at the positions where these photons would normally occur on the visible section of the electromagnetic spectrum. Finally, as you can see, the black lines are exactly at the same positions where the colorful lines appear on the emission spectrum of the given gas, because they correspond to photons that carry the same amount of energy. This final point